Hello everybody, my name is Dimitri.
Kyle.
I'm Asif.
Charles.
And today we'll be presenting to you our design project for MECH 532. The goal of the project was to maximize flight time or endurance of a small light aircraft. Thus, we picked a baseline design from a glider, which is typical, which is a typical sort of plane that maximizes flight time.
Right. So the way we went about doing this is we just built a quick in-house Excel tool, which gave us basic stability and performance metrics. So by inputting geometry into this tool, you could quickly see whether your airplane was stable and whether it had enough lift and some basic drag properties. Once you get something that you like out of this Excel spreadsheet, we got XFLR for more thorough analysis, and then you just go back and forth between XFLR until you get a geometry that you're settled on. And then we finally used eCalc as suggested to get a proper flight time out of this. Yeah, so that's it. Let's show the spreadsheet. Right, so this is the main page to this spreadsheet. So there's all our geometry here. We're able to modify a bunch of these parameters, and then including the location of the payload, and then it spits out our mass and the mass of each component, the center of gravity of the airplane. It calculates that for you, and it basically also gives you a little indicator of the parameters you're interested in, the most important ones.
Right, and since everything is linked together in the spreadsheet, this sheet took care of the aerodynamics, for example, took all the theory from literature, Raymer, class, etc., and spit it out, CL values and CD values for takeoff and landing, which we found to be the most critical points of flight. And then eventually, depending on the speed that we're going at, whether cruise or takeoff, we would get our lift or drag and our aerodynamic performance of the aircraft, which we would then later use to make sure we were meeting the design criteria.
All right, so besides using aerodynamic qualities as a criteria for validating our geometry, we use stability. So everything in gray are variables required to calculate our stability parameters, which are all things we covered in class. So these are all calculated using stuff for the parameters. And down here is our condition for stability. So if everything is green, we can quantify our current geometry as successful. So all the stability conditions are met, and we can actually move on from here into actually simulating our plane inside XFLR to get more meaningful and more thorough analysis. So quickly, we're just going to go over the comparison between our theory and what XFLR gave to us. So we used two solver methods in XFLR. LLT, lifting line theory, which actually only considers the wings of the plane, which actually does align better with our theory, because the theory coming from the Raymer textbook is very wing heavy. Does not consider the empennage, which VLM1 actually does. And in order to satisfy our stability conditions, we had to utilize the vortex lattice methods to calculate our stability conditions within the XFLR software. There is a bit of a discrepancy between VLM1 and lifting line theory. That is due to the fact that we have an existence of an empennage. And also the airfoil that we used, you have to calculate over a larger value of Reynolds numbers in order to actually satisfy the numerical properties of VLM1. Right. So that will take you into XFLR to show our performance output.
Yeah, so here you can easily see the VLM1 simulation done on our aircraft, which just corresponded to the values previously. So we have a very high lift-to-drag ratio, which is expected for high-performance gliders to maximize endurance. And yep, that's basically it. So I'll pass it off for stability analysis now.
Yeah. So for the stability analysis, we found we kind of estimate the neutral point by changing the position of the center of mass, and by changing the position of mass, we got the slope to be 0. At that point is the neutral point, and then after finding the neutral point, we calculated this the static stability, static margin. Using that static margin, we got a 44% static margin, and which is good for our longitudinal stability. and after that we went to the dynamic stability, which is
1 second, got it.
This is calculated directly from our XFLR simulations.
So yeah, like as is outlined like in the report, like we're not going to show all of them, but absolutely all the modes are stable, with the exception of the spiral mode, of course. Yeah, and one thing to note is that the roll subsidence mode has an eigenvalue of like -1000.
As you can see,
It
quite
just
fast.
instantly converges. I think that's due to the large wingspan that we have. So yeah, all poles are on the open left-hand plane. Not much more to say about
Not
this,
much
really.
more to say.
And before we move on, just a quick segue back to this plot. Just a condition for us for stability is that both of the slopes of these plots have to be negative.
Okay, so once we've converged to a geometry in XFLR5, we basically get the drag properties out of it. We treat the CD that it calculates as, the CD that we use in eCalc. So putting all of our geometry, all of our specs, there's really not much input to put here apart from the coefficient of drag. Everything else is not a design variable. Just interpolating between these 2 points for 54 kilometers an hour, which is 15 meters per second, which is a cruise speed. We get a flight time of about 80.2 something minutes. So yeah, that's the biggest flight time we could get.
Achieve,
Right, the flight envelope. So according to our calculations, we get a ceiling of 20 kilometers, which we recognize as practically high. For reasons like we'll probably lose radio signal because it's remote controlled aircraft. It probably won't have the battery life to even get up there. And who knows, maybe the atmosphere is extremely turbulent on the way up. But so this flight envelope is literally just the theoretical values where the propeller can generate enough thrust to support the aircraft's weight. So technically that's possible till 20 kilometers, but practically that won't be the case.
Right. And basically our plane can, any region inside the red lines is where our plane can successfully fly in theory.
Alright, so finally this is a CAD of our plane, little rascal,
Little rascal.
little sweet little guy, nice carbon fiber wrap, looking great.
Mm-hmm.
Right, so to conclude, here's a summary table with all of the results of our plane that was optimized at cruise for 15 meters per second with a final weight of about 2 kilograms, with a pretty small wingspan, a pretty small wing area, pretty large wingspan, so high aspect ratio plane with a very large lift to drag ratio of about 24.
Yep, I guess that's it.
Awesome.
All right, thank you.